Hello, hello. I see my first viewer, and I just turned on the polls. So go ahead and enter your names if you like, or anonymous nickname. And as usual, the burning question is, what's the temperature in the college math room? Math room. Let's see, we got a balmy 51 degrees in here today. Very nice, very nice. Oh, hey. Oh, right, I'm not supposed to say the names. Okay, I'm not gonna say your names because I make the videos public, just in case this helps anybody else out there in YouTube lands learn differential equations. But it is very nice to see you, and you can see each other's names popping up on the poll. And we'll probably give it a couple minutes to get more people into the room, and then we will warm up with a few practice problems that are related to some of the questions on the concept quiz that's due at the end of today. I got some fun activities to warm up with those. And then as usual, just asking you what kind of questions you want to see. And I have filled up all my markers now with fresh black ink, so I've got lots of ink ready to take your questions and work with you as we learn. We're on a calculus adventure now. Up to 5 viewers here, and I think that's including me, so it looks like there's 4 students in the room, now maybe 5, and I'll just wait a little bit longer for some people to come in. Maybe they went to get a snack. I filled up my water. Don't forget to drink water. Hopefully you're enjoying the little adventure in calculus we're having over these couple weeks here. Next week's gonna get even more calculus-y. Yeah, and then we'll get straight back on the road to talking about mathematical modeling. Oh, hey, you guys, you gotta be quiet. Yeah, I'm doing the videos. Don't shout, and please don't scream when you're riding your bike across here. Okay? Do you want to be on the video? Okay, well then get out of here, please. Thanks. Okay, sorry. That was my 8-year-old, and he's riding his bike around. So in case you hear any screams, it's probably okay. It's just a kid having fun in the sun. Don't worry, we're gonna have plenty of fun in here too. And maybe looks like we've got about 7 people joining us now. So let's start with the warm-ups while we wait for others to join. The first couple questions, these 2 questions are meant to help people understand the relationship between continuity and differentiability. And that's one of the things that we were introduced to this week. So if you'd like to get started, just leave your poll response open, and you will see this question right here. It says, click a point on the graph that is not continuous and also not differentiable. So you see that graph come live for you on the live polls. One thing is that I have show responses off right now because I don't want other people to just parrot back what they see. And so I'm going to wait a little bit longer. I see the results adding up. We've got 5 results so far. Maybe wait till that gets closer to the number of viewers, and then I'm going to show the responses, and we'll talk it out a little bit how continuity and differentiability are related to each other. Okay, looks like we got 7 people responded, so let's see what people are thinking. Right, you're all right on the money. Oh, why bother? We don't even need to talk about it. Okay, so you all picked that little jump spot. You can see that occurs when the input variable is equal to 1, and that is a point discontinuity. I'm getting word that one person can't find the poll link, and if you can't find the poll link, can you please go to the math module for this week and go to the YouTube Live April 23rd page. It's the same link every time, so you can bookmark it if you want, but every time we do this, you'll see 2 links appear on the YouTube Live page. The first is going to be the link to the live stream that turns into the replay after it's over, and the second link is the live poll questions link. So if you want, you can use that, but also you can just go to the link. I'll just say it. It's polev.com. Oh, actually, maybe I shouldn't say it, right, because this is public. So I only want our students joining, not necessarily everybody in YouTube land. So actually, I'm not going to say the link. I am just going to let you find it in our private class Canvas page, and hopefully you found it there. Great. So this first question here, or the second question here, right where I have the graph, most people clicked on the spot which is showing the jump discontinuity. And so many people clicked on it, in fact, that it might be a little bit hard to see it. So I'm going to hide the responses for a minute. So you can see that we have when x is equal to 1, when the input is equal to 1, there's a little jump, a little gap in the function. And that's a point of discontinuity. And so if it's discontinuous, that's the same thing as saying it's not continuous. And how that's related to differentiability is that if a function is not continuous at any point or value, then it is also not differentiable. So not continuous implies not differentiable. That follows from it. So that's why everybody picked that jumping point there. But the second question now, I'm going to activate that next question on the poll, is to find a point on that same graph that is continuous. So it is continuous, but it is not differentiable still. And that's a part of the relationship that's a little more subtle, but I thought maybe needed a little more talking out, because even though we can understand that if it's not continuous, there's no way to take the derivative. Is there still places where you can't take a derivative even when a function is continuous? And that is actually possible for certain places. We talked about it in the video, and they discuss it in the book. And in the video, you saw that there's two different ways that it can happen. A place where a function is continuous, but it's still not able to take the derivative. One of the ways is going to be a very sharp corner, and the other way is going to be when a function is going up so fast that it would actually have a vertical tangent. So that second way, where you would see a vertical tangent, if you're curious about that, I'm going to draw an example of that on the board. And the first way, I've got it inside the poll going on right now. So just to highlight another way that it can be continuous but not differentiable. If you consider a graph of the function y is equal to x to the 1/3, that's also the same thing as saying the cube root of x. So if you take the cube root of x, you get a function that looks like this. And right here at the point x equals 0 on this function, right here, the function is continuous at x equals 0, but it's not differentiable. And that's because it has a vertical tangent. Vertical tangent. Okay, so I was wondering if anybody might ask that. There's a question in the homework that asks you to bring in your own examples, draw pictures of things that may be continuous but not differentiable. And so there's two ways that can happen. One of these is the vertical tangent way that I've drawn on the board here. So you just draw a function that changes so fast that it's actually going and it's undergoing a vertical change at some point in the graph. For example, the cube root function at x equals 0. That's one way. And then the other way I'm showing in the polls right now is the way where it's getting a sharp corner. So some people are saying they can't add their name. Oh, right. So if you can't add your name to the word cloud, that's because we've moved on. So I had the word cloud up. I started at 12:45, and I had that up for the first 3 or 4 minutes, and then I moved into the warm-up questions. So everyone, please use the link that you see on the Canvas page. And the thing about that link is that it's changing every time I move on to a new question. So it's okay. We've moved past the word cloud question, but I'm glad that you're here still. And even though I invite everybody to throw their name into the word cloud at the beginning of the session. It doesn't mean that your name is going to show up as we play with all the other polls. So I'm going to show the responses to the current poll right now. And you can see that a lot of people have picked that sharp corner that I was actually graphing the absolute value function to get that sharp corner at x equals 0. And that's a place where it's continuous but not differentiable. And you'll notice that even though we see the little green markers there, they don't have your names attached to them. So you don't have to worry about being called out or anything when you're entering your names and your comments. Those aren't attached to your poll responses. But I can only have one poll up at once. So that's why I've got this poll right now, which is asking you to find a place that's not differentiable, but it is continuous. So as we were just saying, if a function is not continuous, then it follows, it implies that the function's also not differentiable. But if a function is continuous, it doesn't necessarily mean that the function will be differentiable. There are still some places and some functions where we have the continuity in place, but we don't have differentiability. And those are sharp corners and vertical tangents. Those are the two instances. And so everybody's pointing to the sharp corner on the absolute value function that occurs right there at the origin at the input equals 0. And that's the correct answer to that poll. Okay, cool. So let's see. I think I'll put it back on the word cloud just for a minute because now I have 11 viewers, and I think that people kind of want to put their names into the word cloud. So just for a second here, you'll see that your same poll link that it always is, it changes when I change which question is active. And now I put it back on the word cloud to give people who have just joined us the chance to add in their name. So welcome everybody, and I'm glad to see you here. I just stopped saying the names on the video because I make the videos public. College math is really getting popular now. Well, maybe not relative to other YouTube pages, but I have like over 600 subscribers, which I think is amazing. It's been around for 4 years since I started online teaching. And so I thought in case any of the other subscribers want to make use of these videos, I make them public. And so for that reason, I will not say any student names or any other student information inside of these videos. But I see your names popping up in the polls. The polls are not public. The poll results are only visible to students in the program who are accessing the polls through our Canvas page. And so I'm also viewing the results on there, and I see you in there, and welcome. I'm glad to see you here. Okay, so I hope that everybody understood the difference, or the connection, I should say, between continuity and differentiability from those first two practice questions. You'll see a similar question in your concept quiz today. And then I just have one more practice question that I'm going to do, and that one has to do with sensitivity. You'll see in the book they have a section that says variables other than time, and that starts on page 75. And inside that part where we considered the derivative in terms of variables, input variables other than time, on page 78, there's an example of sensitivity. You're going to see that they have an example that has to do with the response of cancer cells to a drug that's supposed to kill them. And now I'm going to activate my next question here, which I got this off the internet by searching for sensitivity biological examples. And it says, click on the graph where flies are most sensitive to isoflurane. So I guess isoflurane is some sort of chemical that makes flies get anesthetized or put to sleep. And there you see the classic sigmoid curve that we were already talking about quite a bit this week. And it's so, that sigmoidal switching type behavior is so ubiquitously found in many biological applications. And so I thought, oh, let's go back to there for a minute. And you'll see on page 78 that it says that the concept of sensitivity is tied to the derivative, because it's saying, like, how is one thing reacting to a little bit of a change in the other thing? So if I change the input variable, if I increase the input variable by just a little bit, how much or how little is the output variable going to change in response to that? And that's called sensitivity. And on sigmoid curves, the most sensitive part is I don't know if you remember. Let me see. Let's see what the responses are. Oh, wow. Okay, all over the place. So this is now I'm finding some places where I can talk a little bit more about it. There may be some issues about sensitivity. That's great. So let's talk about sensitivity a little bit. And if you have a book with you, please turn to page 78. It's at page 78 on the book where you'll see they talk about sensitivity. And it says the concept of sensitivity is really talking about the quantity dy dx, or the derivative. So when I say where on this graph are flies the most sensitive to isoflurane, that means where is the derivative of the graph highest? Okay, so we're going to look for the place where the derivative, the value of the slope of the tangent line on that curve, is the highest that it can be. I'm going to clear the responses. If you're looking at the responses right now, you see that there are 10 different markers, and they're all over the graph. Comparing that with the previous two polls, all the markers on the last two questions were all in the same place. Sometimes I like to call that consulting the cloud, because the cloud of points, if everybody understands what I'm trying to teach, then that cloud of points will all show up in the same place. But when I see that the cloud of points is everywhere, so spread out, it means we need to dive in a little bit more. So I'm going to clear out the responses, and I'm going to write that sensitivity means the value of the derivative on the board, and then we'll have you input the answers again and see if that clears it up. Okay, so I'm clearing the responses now, and I'm hiding the responses so we can't see them. But I'd like you all to try again, and I want to see if the cloud of points can all converge on the correct answer by going into it a little more detail. Sensitivity. The derivative. Okay, sensitivity speaks to the derivative because it's talking about the rate of change, right? Sensitive means like if I change the input just a little bit, are you going to react really wildly to it, or are you going to do basically the same thing that you were already doing? And so that's because the rate of change says how much or little the output is reacting to the input. Okay, a lot of times sensitivity and its relationship to the derivative is used in examples where the input variable is something other than time. And that's because time usually goes in one direction at one speed. Time is just time, right? So that doesn't make as much sense as an example here with like drug delivery or something else, some kind of example where we're able to manipulate the input, right? Because like the amount of isoflurane that I gave the flies, I could have given more, I could have given less. And so I'm able to travel back and forth in this input variable as much as I please. And I'm trying to figure out how fast the output or how slow the output will react or will change as I start to move the input a little bit to the left or right. I'm going to draw the sigmoid curve on the board too so we can talk about it. And again, keep in mind that this type of S-shaped curve that I'm calling a sigmoid is really, really prevalent in biology. You're going to see it throughout this book, and probably in a lot of other textbooks if you're studying biology. And so that's why I want to focus on this type of sigmoid curve so much. Because you're going to see it all over the place. Okay, and so in this case of drug delivery, maybe this is like the drug amount. And this is like the percent of flies that are asleep or anesthetized. Just as a little aside, has anybody ever gotten a fly on a leash? because you can put flies to sleep by putting them in the fridge and cooling them down. If you put them in the fridge, they'll go to sleep and they'll stop moving. And if you catch a really big fat fly and you put it in the fridge and let it go to sleep, then you can tie a string on its leg while it's asleep. And then when you bring it back out of the fridge and warm it up, it'll wake up again, and then it'll be on a leash and you'll have a fly on a leash. Go ahead and look that up on the internet on your own if you want. It's pretty hilarious. My son has tried to do it a couple times, but we accidentally used the freezer instead of the fridge, and it doesn't come back to life in the freezer. So anyway, we're still experimenting with anesthetizing flies in our own house. In our quarantine staycation, we got to find other ways to do science at home, right? So I thought I'd bring this example to the class. Where are the flies the most sensitive to the drug? Sensitivity is another concept that's totally related to the derivative. It looks like only 5 people have put in their answer, but let's show the responses, see what people think after the explanation. That's a lot better. Yeah, and so this is learning in action. That's great. Now you can see if you look at the responses that the responses are really clouding up right around this region right here. This is where the curve is the steepest. This is the steepest part. The steepest part of the curve right there is where the derivative, which has to do with the slope of the tangent line, is going to have the highest slope. Okay, so like if I pretend that I'm going to be drawing tangent lines in red here, you can see the tangent line here has a low slope. Here it has a higher slope. Here it has a higher and a higher slope still. And then when I get to this top plateau, then it seems like the slope starts to lower a bit again. So which part of the curve here has the little red tangent line that has the steepest or highest slope? It's exactly that part in the middle, specifically the inflection point, the place where the concavity changes from concave up to concave down. There's one very special point, and calculus can help us find that point. There's going to be one special point called the inflection point. And the inflection point is the place where the rate of change peaks, where the slope of the tangent line is at its highest possible value. And that's tied to sensitivity because that's the place where you're going to get the most bang for your buck, which is to say that if I drop a little bit more drug in right here, I'm going to get a huge increase in the amount of flies that I put to sleep. So the flies are reacting really sensitively to the drug amount at this part. Maybe I'll understand it better if we compare that to a couple other places on the curve. For example, if I just have a little bit of drug here and it's not really working yet, if I add a little more drug here, it's only going to start working a little bit more. If I add a little bit more drug here, it's going to make a huge difference in the percent of flies that I put to sleep. Over here in this zone, I've already done them all in. I've already put all the flies to sleep. And so kind of like at the bottom of the curve, the top plateau is the same as the bottom plateau. It's a plateau. So its derivative is going to be really low. And that's a place where the flies are not that sensitive. Now you may think that up here is a place where the drug is really effective. And it's true, but effectiveness is different than sensitivity. Effectiveness means that I've used so much drug here that all the flies are asleep. But how sensitive are the flies to a little bit of change in the drug? If I'm already over here and all the flies are already asleep, if I add a little bit more drug, the flies are still going to be asleep. It doesn't really change their reaction. The reaction is responding very heavily here in the sensitive zone where the derivative is highest. Okay, good. I hope that helps. I see somebody adding into the chat window here a question, so I'm just going to pause and look over the question for a second. As I look over the question, though, I'm going to also turn on the next poll because that was fun. That was fun warm up for the quiz today, but really what I want to get into is what questions do you want to see? And so now I've turned the poll over to the brainstorm, the classic brainstorm question of what homework or exercises would you like to see me do on the board? And while I'm waiting for that to populate, I'm going to read over the comments, see if I should share those out to the group. Yeah, so I'd like to share this question with the group while we're waiting for people to put in requests into the brainstorm poll. And it says, is it fair to say that sensitivity is asking not what concentration leads to a higher amount of flies effective, but what concentration leads to a higher rate of change in the flies being effective? Yes, that's exactly what the question's asking. When it says where is it the most sensitive, it means where is the rate of change the highest. I think it might also help if I explain what the rate of change means in words for this equation. And I'll do that to finish it off while I'm still waiting for people to put in questions. I don't see anyone putting in questions yet, so I'm going to wait for that. Okay, so here I'm going to erase this part and explain out what I was saying a little bit more. Okay, so I'd like to name some variables here so I can start to interpret the derivative as an expression. Let's call the drug amount capital D, and let's call the number of flies F. Okay, and so this curve right here would be a curve F of D. So the input variable is D, and the output variable is F, which is the percent of flies that are asleep. Okay, and so the derivative of this function is called F prime of D, right? This is using the prime notation, but we can also denote the derivative as D capital F, D capital D. So the change in the percentage of flies that are asleep divided by the change in the amount of drug that's given. Okay, so this is the change in percent of flies divided by the change in the amount of drug. Okay, and I don't actually have a numerical or algebraic form for this equation, so I'm not actually going to get an expression for the derivative. But I'll just put in some fake numbers just so we can play around with this a little bit more. Let's say that this drug amount right in the middle here is like the value of 5. I don't know, 5 what? 5 micrograms or milligrams or whatever units are appropriate. And then maybe this down here is 1, and maybe this up here is 10. Okay, so let's say that if I evaluate the derivative at 1, I get something like, I don't know, 2. And then if I evaluate the derivative at 5, I get like 12. And if I evaluate the derivative at 10, maybe I get 1. Okay, I'm just making these numbers up, but a lot of the exercise sets also ask us to practice approximating the derivative by using successively small values for dt. We'll go into that more later. But let's say I did something like that, or perhaps I used derivative rules that you'll learn next week on the algebraic form if I had it, and I got these values out, okay? Remember that the values that I'm getting out for the derivative speak to what's the percentage change in the number of flies versus the change in the amount of drug that I'm giving, okay? And so right here, if I'm going to say that f prime of 1 is equal to 2, that means when I'm giving, let's call this milligrams. Let's say that it's in milligrams, right? So what this would say here is when giving 1 milligram of drug, increasing an increase of 1 milligram leads to a response of 2% more flies put to sleep. I don't think we practiced this enough this week, but I think it's a really helpful exercise to look at some values of a derivative and then try to write down a sentence in context that kind of explains what that derivative means. I think that'll really help you to understand the question. And so I'm going to read out what I wrote. I'm sorry if you're having trouble reading the board. I was hoping that it would at least be legible today. Dang it. People are saying they can't read the board. Let me try something new. Thanks for the instantaneous feedback on that. I'm gonna try to move my whole setup closer to the board and just show one side of the board at the time so that hopefully you can read the board better, okay? Bear with me. This might get a little shaky. I hope this helps you read the board better. I'm sorry about the low quality internet. But if I move it closer, and maybe you can tell me on the chat, can you read what I wrote now on the board? Yeah, so if anybody who says they're having trouble reading the board wants to just let me know, I'd really appreciate it. I moved it closer. You can't see the whole board, but this, okay, great. So we'll just work with it this way where I'll just show half the board at the time so that you're able to read it. Okay, great. All right. So if that's better, I'll just keep doing that from now on, even though I'm a little bit squished up here, but that's perfectly fine. So let me give you a snapshot of what that first board was saying. And I guess I have to move the computer. Right. So here's the sigmoid curve that we were talking about. Here is the steep part. That's where you see that everybody put in the answer for their poles as the place where it's the most sensitive. And then I started to put some variables on it where I said the drug amount is D, and I'm just going to say in milligrams just for fun. And then the output variable is F, and that's the percentage of flies that are asleep. And so I have a function, percentage of flies that are asleep, as a function of how much drug I gave them. And then I'm going to write down some made-up values for the derivative, and I'm going to interpret those with sentences to help you understand the derivative better. So first, you can see the little made-up examples that I put for the derivative. I'm just going to say that if I evaluate the derivative when I'm giving 1 milligram of drug, I'm going to get 2. And so that means that if I look right here where my input is 1 milligram of drug, and I draw the tangent line there, the slope is going to be 2. It gets most blurry when you get close to the camera. Okay, so thanks a lot for the input so that we can try to make this a good experience for you. People are telling me that it's best if I stand towards the board, don't get too close to the camera, and then it'll be a lot clearer. Yeah, because I think it has an autofocus thing. Okay, cool. I hope this is working for you. So that's what I'm trying to say with this statement that f prime of 1 is equal to 2, is that the slope of this red tangent line, I'll draw it again so you can see it emphasized. If I draw a tangent line right here to the curve, centered here at the point 1, then the slope of this red tangent line at the point 1 will be equal to 2. And what I'm trying to say with these other two statements is a very similar thing, is that if I then go equal to 5, so I'm giving 5 milligrams of the drug, and I try to draw the tangent line right there, then that's going to be a much steeper tangent line. And because that tangent line is so much steeper, that's why I made up the value, but I tried to make it in line. Compared to the value of 2 that I had before, I'm saying it went all the way up to 12. So it's a lot steeper. And then for my last one, if I evaluate what's the sensitivity or what's the derivative when I'm giving 10 milligrams of the drug, then you can see that the tangent line that I would evaluate at the point D is equal to 10 is very shallow. It's much more shallow than this steep part, and it's even a little more shallow than that first one I evaluated, and that's why I made up that the value would be 1. So hopefully you can relate geometrically these algebraic statements about evaluating the derivative at different points to the slopes of the tangent lines that we're trying to draw on the graph. Okay, now I'm going to move it to the other side of the whiteboard so you can see me writing in the explanations of what I'm trying to actually explain in words with that. Great, people are telling me that's really visible, and so I'm really happy to hear that. So what I was trying to say is that in this context, the derivative is the sensitivity. And so whether we call it f prime of d or we call it df dd, the interpretation is that that's the change in the percentage of flies that are put to sleep as I change the amount of drug. So it's the rate of change at that point. So let's say that I just evaluated here for f of 1 is equal to 2. And let me use I'm going to use a little where the numbers from here end up being. So the slope was 2, right? So I'll use the same red for that 2. And the input variable, maybe I'll use green for that. So at the point 1, I get f prime of 1 is 2, okay? So what that interprets to is when I'm giving 1 milligram of drug, you see the 1 in here that's in green? That's the 1 milligram of drug, when I'm giving 1 milligram of drug. Well, what happens is the concept of the rate of change is that for every increase of 1 input unit, I'll get an increase in the output of whatever the slope value is. And so at that point, at the point drug is equal to 1 milligram, an increase of 1 milligram will lead to a response of 2% more. 2% more flies put to sleep. Okay, and that's because it's a rate of change description, right? So if I said my car is going 45 miles an hour, that means if I went for 1 more hour, I would go 45 miles, right? So at this point, if I increase the drug by 1, I would get 2% more flies put to sleep. One thing I want you to notice here is that I did not make this number 1 green, because this number 1 is going to stay a 1 even when I change to evaluating it at different points. Because that number 1 right there is similar to the going for 1 more hour. Whenever you talk about a rate, the easiest way to understand a rate is thinking about what would happen if you went for like 1 more input unit. Okay, so that second 1 right there is always going to be black because that's always going to stay the same. But let's go on and do this for 2 more examples. Okay, so if the input is 5 and the output is 12, the derivative, I'll say the derivative value is 12, then what it's going to say, the interpretation is when you're giving 5 milligrams of drug, you see, so the input here ends up going into the interpretation sentence right there. If you're at the point when you're giving 5 milligrams of drug, then how to interpret this number 12 is what it's saying is if you increase by 1 milligram at that point, you would get a response of 12% more flies put to sleep. That's why I was saying it's more bang for your buck, because the buck here is the $1 or 1 unit that you would increase the X, and then the bang is the response, which is the derivative value. Okay, so you notice I didn't change this number 1 because it's always a concept of, okay, if I moved over in the X by 1, how much would the Y change? And it would change by the derivative amount 12. Okay, and so for the third example, same thing again. If the input is 10 and the derivative is equal to 1 at that point, what it means is that when I'm giving 10 milligrams of drug, when I give 10 milligrams of drug now, how to interpret this number 1 right here is that if I increased my dosing by 1 milligram at that point, I would only get a response of 1% more. So this is how many more percent flies you'll get put to sleep if you increased your drug amount by 1. Every time you're thinking about this concept as if I let the change in the amount of drug be equal to 1, then the numerator is going to be the same thing as the output from the derivative. So that's how much it's going to change. And hopefully going through those 3 sentences allows you to really understand why we're saying the derivative is like the sensitivity. Because it's in this zone right here, where if we went from 5 milligrams to 6 milligrams, we're going to get 12% more put to sleep. But if we went from 10 milligrams to 11 milligrams, we're only going to get 1% more put to sleep. If we went from 1 to 2 milligrams, we'd only get 2% more put to sleep. And so it's that increase right here at 5 and that zone of very steep increase of the curve that the response is most sensitive to a change in the input. That's why it's called the sensitivity. Cool. Hopefully that was really helpful to explain that concept, which I think is really important for biology. And now I'm going to go over to the polls, and I'm going to see what kind of questions you want answered. Okay. So what I'm going to do here is I'm going to go, I've got requests for 2.3.4, and I've got a request for 2.2.7, and a request to understand the average rate of change in derivatives more geometrically. So I can probably help you understand average and instantaneous rate of change more geometrically as I move through the other problems. I'm going to go ahead and look at what those problems are and see if there's a natural order to those, or if I should just take them as I see them in the polls. Okay, so one of these questions is going to be showing you how you can use successive approximations as delta t gets smaller and smaller to approximate an object's speed when you're given its position function. So that's what I'll do for 2.2.7. And then in 2.3.4, it says to write the equations in slope-intercept and point-slope form for lines where you're given either the points or the slopes. So actually 2.3.4 is actually a review question that's covered in pre-calculus. But I'm happy to go over that question for you. I think it's probably more appropriate for me to first speak to the question in 2.2.7, because that's also going to get to the understanding of average versus instantaneous rates of change geometrically. So I'm going to start by explaining more about this falling object example. So what we're going to do right now is, if you're following along in the book, we're going to go to page 27, and we're going to talk about this falling object example a little bit more. And we're going to show you how we can approximate that object's speed at time is equal to 1 using successive approximations. In the book, they try to approximate the object's speed at time 1.5. So when you look on pages 73 and 74, you see t is equal to 1.5 as their chosen time that they want to zoom in on the function. But question 2.2.7 asks us to use a time is equal to 1 instead of 1.5. So that's a little bit of a help if you're trying to follow along with what you see in the book. Everywhere you see a 1.5, you would replace the 1.5 with a number 1 to do question 2.2.7. I'll talk it through on the board, and I'll also mention how average and instantaneous rates of change are related, because that's exactly what we're doing when we're using successively small values of delta t to approximate the instantaneous rate of change using the average rate of change. Okay. Just a second here while I clear the boards. It's fascinating me wash boards, but if you're watching this in a replay, you can feel free to just skip to the sweet parts where there's actual math on the boards. But those who are viewing live, thanks for bearing with me. I gotta wash it with a wet one and then dry it off. And I'm just gonna copy the picture. Now first I'm gonna copy figure 2.3 from the book onto one of the boards so that I can draw the secant and tangent lines. And then on the other board, I'll do a bit of algebra, a bit of plug and chug like you see on page 73. Okay. So first we're gonna go over here and we're gonna draw the picture. And what this is describing is it's an object that starts 100 feet. It's an object that starts 100 feet up in the air, and then I'm just going to drop it. And it's going to drop, but I'm going to describe what its height is as a function of time, where the time is in seconds. So this is in seconds. And then this is going to be the height in feet. Maybe I spelled that wrong, I before E. Feet. And it starts at a value of 100 and then it just drops off. Okay, and actually the functional form of it is that h of t is equal to the initial height. They call the initial height h0, but they've described it using the number 100 feet, so I'll just put 100 feet, and then minus 16t squared. Okay, so if you're one of those physics buffs out there, you may be noticing this number 16 and wondering where that 16 came from. That number 16 is very special. It is the acceleration due to gravity on Earth in the units of feet per second squared. You may also know it as 9.8 meters per second squared, but in feet, it's approximately 16 feet per second squared. And the fact that this takes on the functional form of a down-facing parabola is not by accident. That is actually something that comes out of the equations, the physical equations that assume that the acceleration due to gravity is constant. Acceleration, if you've seen it in the book, is the second derivative. And so you'll make more sense out of this by the end of next week. If we assume a constant acceleration and then we integrate it up twice, we're going to get this type of functional form here. Oops, I misspoke. Actually, the acceleration should be 32 feet per second squared. Yeah, sorry, not 16, but it's going to end up being 16 times 2 or 32 feet per second squared. Anyway, don't worry about it. I think that you'll understand that more after we get into the derivative rules next week. But I just want to highlight that this parabolic form that you learned about in quadratic land from pre-calculus, it comes straight out of the physical assumption that gravity is constant. That's why it falls like a parabola. Same thing will happen if you drink water out of a water fountain. As soon as you shoot the water fountain on, you'll see a parabolic path of the water coming out of the fountain. Okay, so anyway, to get to the question here, exercise 2.2.7 on page 74 says use successive approximations to find the object's speed at t is equal to 1 second. So that's what we're going to do, and looks like when t is equal to 1, that object is at about 84 feet up. So here's time is equal to 1, okay? And then if we just plug in the input of 1 into the function, you'll see that h of 1 is equal to 100 minus 16 times 1 squared, 84 feet. Okay, and so right here, this point on the graph is the point 1, 84. Okay, so its height at the time after 1 second of letting go of it, its height is 84 feet. But how fast is it dropping? That's the question that they're asking. You want to approximate its speed, or really its velocity, which is speed plus the fact that it's going down, so it's a speed including direction. Approximate how fast it's going at that point, and that's going to be the concept of the tangent line. Since we were just graphing tangent lines in red, I'll graph the actual tangent line, but then I'm going to step back and tell you how we're going to approximate it using, as they say, successively smaller approximations. Okay, so what we're going to do here is draw this tangent line. It's not perfect. It's supposed to be exactly a line, a straight line, but it would be the unique line that touches the curve just at this point, 1,84, and it doesn't intersect the curve again at any other nearby points. It's just grazing the point right there. It's tangent to it. And if you look at this line, you'll notice that the line is pointing down. It has a downward slope. And that makes sense because the velocity of the object is negative. Remember when we talked about vectors in one dimension and the fact that they have a magnitude and a direction? The magnitude is the speed and the direction is the sign, whether it's positive or negative. And so I would say that whatever the absolute value of the slope here is, that would be the speed. But negative times that value, including the negative to denote the downward direction, that would be called the velocity. Okay, and that's what we're going to get out of the derivative equation. I can't wait till next week because next week you're going to learn a really awesome rule called the power rule. And with the power rule, you can actually take the derivative of the functional form and then you can just evaluate the derivative algebraically and you can get the instantaneous derivative exactly. That's going to be really nice. But right now, supposedly, as we're learning where the derivative derives from, we are not there yet. And so what we're going to do is we're going to emphasize the concept of what a derivative is. It's the instantaneous rate of change by successively making average rates of change that are closer and closer and closer together. Okay, so now I'm going to erase the tangent line because even though this is a beautiful tangent line that exactly describes the instantaneous rate of change exactly at time is equal to 1 second, we don't have the tools yet. They're in section 2.5. We don't have to take the derivative in algebraic. Okay, so goodbye tangent line and hello secant line. And so hopefully this really helps to explain the difference between average and derivative or instantaneous rate of change. A secant line is something that you had already learned, and it's basically just the slope between 2 points on a graph. So I'm going to pick 2 points. One of the points should probably be 1 because that's where they want me to focus on. And then for my next point, I'll probably pick something that's just a little bit away from 1. So maybe I'll pick, I don't know, 1.2 as my second point. For a secant line, you need to pick 2 distinct separate points. So I'm going to pick 1 and 1.2. Okay, so there's the first point, 1,84, and the second point is going to be 1.2, comma, I don't know, whatever it is when I plug in 1.2. So let me see, h of 1.2 is 100 minus 16 times 1.2 squared. And I'm going to need a calculator for that, so I'm going to just plug it into the internet and see what I got. Oh, sorry, that reminds me. I'm going to turn on the open-ended scrolling now. I really should have done that earlier. I'm sorry if you've been waiting for that. But now that I have enough input on what questions you want to see, I'm going to just leave this open-ended chat space for you so you can, you know, like one of the things I might have asked is, does anybody know what h of 1.2 is? And if you can calculate that faster than me, go ahead and respond to that in the open-ended scrolling so you can get some engagement and interaction going. H of 1.2. You see, I need to evaluate the output of the function when the input is 1.2. So I would just type into a calculator 100 minus 16 times 1.2 squared. So go ahead and let me know if you can get that, or else I can also, I'm just going to use the internet as a calculator. 16. And I don't know if you're playing along with me. Oh, thank you. You're quick. 76.96, exactly. So if you just plug that in, plug and chug, you're going to see 76.96 feet. So what happened between time 1 second and time 1.2 seconds? And inside that realm of just 0.2 seconds it dropped down from 84 feet down to 76.96 feet. So here's this point right here is 1.2, 76.96. That's that second point. And all a secant line is a line that connects those 2 points. So I'm going to draw an orange dotted line that goes through the first point, and it also goes through the second point. You see, so a secant line is a line that connects 2 distinct points on a graph. And just like every other line, it's uniquely defined by exactly 2 points, and it's going to have a slope. The slope of that orange dotted line, the slope of that secant line, is called the average rate of change. So the next thing I want to do is compute the average rate of change. Just to go back a little and compare it to our ultimate goal, which is the tangent line. Remember that the tangent line that I drew in red looked like this. And so if you compare the slope of the secant line with the slope of the tangent line, you'll see that they are 2 different lines. They have similar slopes. They're both negative values, but they're not exactly the same slope. And so what the point of the question will be for me to try to get at the value of the red line slope by, after I calculate this one, trying something that's closer together, and then closer together, and closer and closer and closer together. That's the delta t, the difference between the 2 time points. I'm going to make that smaller and smaller and smaller, and then the orange line will get closer and closer to the red line. I don't know if you've checked out the links to the Desmos activities that I put on the weekly schedule page for week 4, but I've got some really cool Desmos activities in there that have a little slider, and you can slide the points closer and closer together, and so you can see an actual graph and really see how it pans out. A lot better than I can draw it here, okay? But this difference here, the difference between 0.1 and 0.2, that's the delta t. Okay, so for this example, delta t is 0.2 seconds because I started at 1 and I moved over by 0.2 seconds to get to that second part. Okay, so now I'm going to use the second board to calculate the average rate of change. And if you've done this problem again, then you know where this is going. I'm supposed to have to do this again and again and again for all these different values of delta t. So it can get a little tedious, but by next week you won't be in this zone anymore. This is just, it's kind of like Euler's method. It's a hand practice for a reason to really like cement your knowledge and understanding of it, but you're not going to do this in general. You're going to have some rules to help you. Okay, so the average rate of change, which is denoted with AROC, is just going to be the slope, is the slope. And the slope has the normal slope equation. M is equal to, usually people write y2 minus y1 divided by x2 minus x1. That's a form that you've probably seen before when we're talking about x comma y points. And so that's if you're using x comma y, right? Can you see all the way over to there? Yeah, so x comma y. But here we have h of t, right? So our points are, our function is h of t. And so because our endpoint is t instead of x, and our output is h instead of y, our slope is going to be h2 minus h1 over t2 minus t1. And that's because our points are t comma h points. So that's if I'm talking about t comma h. Okay, hopefully that's not too many letters for you, but it's important to make sure that the equations that we're referring to align with the functional letters that we've chosen, okay? The concept's always the same though. It's the difference in the output divided by the difference in the input. And so just to go back to our other board, we had the point 1 comma 84, and then we had our next point was 1.2 comma 76.96. And so we're just going to implement the slope equation there, and we're going to say that the slope, which is equal to the average rate of change, this m right here is the average rate of change between these 2 points. It's the difference in the output So 76.96 minus 84 divided by the difference in the input, which is 1.2 minus 1. Hopefully everybody's following along with where those numbers came from. And then we just have to calculate it. So if you're playing along, the 3 people who gave me the answer, 76.96 for the output at 1.2, maybe you want to help me out here too with what is this? Like what's that number on the top? I know the number on the bottom will always end up being delta t because it's the difference in the time points. So I already know, and it's easy to compute, that that's 0.2. But what is 76.96 divided by 84? And then what's the ratio going to be? So I'm going to do that on my calculator here. 76.96 minus 84. Negative 7.04. Thank you very much. I really appreciate that. So that's negative 7.04 as a difference on the top. It's a negative amount because the thing's going down. Technically, according to physics, the speed would be positive, but the velocity, which is the speed plus the direction, is negative. It's going in the negative direction. And so that's the most accurate way to describe it, is to also include what direction it's going in. And then if you just divide this out, let's see if you can divide that. I'm not going to divide that. But on a calculator, I'm going to divide that by 0.2, and I'm going to get negative 35.2. And so that's what I got there, is negative 35.2. Now, here's a fun question for people who are in the live chat thing there. What's the units on that value? I see that people are entering negative 35.2. That's excellent. But negative 35.2 what? Like, what? That number doesn't really mean much to me if you don't put it in context of the problem and tell me what the units are. And so I want you to tell me negative 35 what? Seconds, feet, some kind of ratio of those two things. Actually, that's another question that I put on the concept quiz. So this is good review for that. And you got it exactly right. It's feet per second. Yeah, it's always going to be the output variable units divided by, or per, the input variable units. Right. And so since the output is in feet, the input is in seconds, it's feet per second. Exactly. Feet per second. Right. And so that is exactly the average rate of change between these 2 points, but that is only approximately an approximate value of the derivative, right? So this is only an approximation, only approximates the derivative, which would be h prime at 1. What's the actual derivative? What's the instantaneous rate of change? Exactly the velocity that it's going just at the time point t is equal to 1. It's going to be close to negative 35.2 feet per second, but it's not going to be exactly equal to that because that's just an average, not an instantaneous rate of change. Going to an example from driving, let's say that you have to go 100 miles and it took you 2 hours to get there. You would say that your average speed is 100 miles divided by the 2 hours, so 50 miles per hour, because you have 2 separate time points, right? You have 0, 0, and then after 2 hours, you went 100 miles. So that would be your average rate of change, or your average speed. But when you're actually driving in your car and you look down at the speedometer, that's telling you how fast you're going just at that instant. Because when you on-ramp onto the highway, you're accelerating, right? And then you're probably going on the highway like 65 or 70, and then you slow down, and then you hit a light, and you're stopped, and then you get to your destination. You weren't going exactly 50 miles per hour the whole time. So the instantaneous speed you're going is the information that's given by viewing your speedometer exactly at that moment. So let's go back to the graph and we'll talk about the geometry of the derivative versus the average rate of change. Okay, so over here we have the picture. And like I was saying, what we just computed was that the slope on this orange dotted line is negative 35.2 feet per second. But what we're really after is what is the slope of this red tangent line that gives us the instant rate of change. We would have gotten a lot better of an approximation if we had moved this second point a lot closer to our first point, okay? And that's what they mean when they say use successive approximations. Now you may wonder how many successive approximations, because I just did like a whole board of work just to do that one. How about 3? That seems kind of reasonable. At least 2, okay? Don't just use 1. Although I know it's tempting because hopefully by now you're getting the feeling that, you know what? The closer I make this point to that point, the smaller of a delta t I choose, the better the approximation is going to be. So I don't actually have to make a lot of successive ones. I have to get really close to get a good approximation. It's just like on Euler's method. When you want to approximate the trajectory by numerically integrating it with Euler's method, you want to choose a small delta t, because a small delta t will get you closer to the real answer. Okay, so how you would do the rest of this problem is you would just do it again with a smaller number. I'm not going to do the whole thing again because I think people might get tired of hearing me talk about it. But let's say that I had used t is equal to 0.01 instead. If I had gotten that close, then I would have been talking about a point that's right here, 1.01. You see, and that would have been a lot closer to my initial point. And then these 2 dots would have been a lot closer together. And then the orange line would have looked a lot more like the red line. When you're starting to get really that close, it's better to have a real graphing tool. That's why I provided those links to those Desmos activities. So please take a look at those links, especially the second link to that second Desmos activity. And I made a video of myself using it to help you to figure out how to use it. Where all these calculations that I just did on the board, they're just going to pop out of the Desmos. Somebody had already programmed it in there. And then you're going to see that as you get it closer and closer and closer, that number is going to converge. It's going to get closer and closer and closer to the instantaneous rate of change. Okay, hopefully that really cleared up the questions that people were asking for there. All right. And so I'm going to go on to 2.3.4, which was the other request for today. And then if I have some more time and if people are curious, some people seem interested to talk about the properties of linear maps. And that's something that they talk about in section 2.4, linear mapping. And it is important conceptually for the types of models that we're going to go back to in chapter 3. But it might be the least concern on people's list of things to do if they're trying to work on the homework set. Because I see someone asking about 2.3.4, in which they have you practice writing the equation for the tangent line. And that's an important calculus skill. They have people go through that motion a lot in calculus. The whole reason that they have you write the equation for the tangent line is so that you can follow the tangent line and get an approximation of where you're going to end up next on the function. And that maybe reminds you of Euler's method a little bit. I'd like to just bring it back for a moment. It's like, why are we doing all this junk? I thought we were trying to model. Look, I'm America's Next Top Modeler. I've got my modeling scarf on right now. So what are we modeling, right? What happened to our state equations? Well, the state equations from chapter 1 are equations that give you the value of the derivative. And when you implement Euler's method, you're doing a linear approximation. That's what they talk about in section 2.4. And in order to do a linear approximation, you need to know the expression for the line to some degree. And that's why they're asking you to go through that exercise in 2.3.4. So let's get into that a little bit. And don't forget that if you look at my playlist for this week, the second video in my playlist is a 5-minute video that just talks about how to find the equation of the tangent line when you have a value for a derivative at a point. And so that's another place where you can see this kind of information, but I'll do 2.3.4 so that it's exactly in the same format. I'll just get this out of the way too. Well, it's not distracting. Okay, so for those who are still following along, I'm on page 83, talking about exercise 2.3.4, where it says write equations in slope, intercept, and point slope, different types of form, because I think they're the same thing. It's like the equation of a line is the equation of a line, but we have these two different ways to express that equation of a line. So let's go over that just a little bit. Don't forget that the open-ended chat space is still open. So as I'm going through this, if you have any questions or anything you want me to elaborate on, if you want me to go faster or slower or something, just type it into that chat box and I'll be able to see it. Okay, so let's go over a little bit. What's the difference between slope-intercept form and then point-slope form? I actually have to read it because I never memorized the words for this. But slope-intercept form is the form that we're used to. That's the y equals mx plus b form. And so that's y is equal to mx plus b. I guess I could see why they call it slope-intercept form, because you can see the slope right there, and you can see the y-intercept right there. So that's the slope-intercept form. And then the other one is called the point-slope form. Okay, and then it says the point-slope form looks like this. Y minus y0 equals m times x minus x0. The heck is all that stuff? This form arises, this form is easier to write down if you have the slope in your hands and you have been given an x naught, y naught, some point to start with. Okay, let's see. For example, I'll do part B first, because part B is the time when you would want to use, actually, sorry, I'll do part A is where you'd use this form, part B is where you'd use this form, and part C is where you just got to choose whichever form you want. Okay, so the choice of which form you'd want to go for first may depend on which way the information is being given to you. Okay, so let's do part A, where they give us the slope and they give us the y-intercept. So that's why it's easiest to use the slope-intercept form. Okay. So here, I'll just erase it because I don't feel like moving the whole board. I don't want to move the computer over. Like I was saying, for part A, they give you the slope and they give you the y-intercept. So if you have information like you're given in part A, where they're given the slope and the y-intercepts, you just throw it into the slope-intercept form. So y is equal to 2 for the slope times x minus 54 for the y-intercept. That's easy enough. And then it says to write it in the other form too. I'm feeling a little bit of regret. I'm sorry that I did this to you, because honestly, if I have it in this form, I rarely would I ever want to write it in the other form. But I guess I'll force myself to, because I want to do what the book says. Okay, fine. So the other form, which is the point-slope form, is the form where it's easier for me to do if they give me the slope and a point. So I need a point to get into point-slope form. Well, what point do I have on the line? Let's use the open-ended chat. I'm going to ask for your support here, because maybe I'm not having my most fun time with this question right now. It's just a bunch of algebra. What point, can anybody who's still out there watching me name one point on this line? Maybe a really easy to name point. They give me an XY point, because if I did have an XY point, then I would throw it into the other form, which is the point-slope form. So if I wanted to do point-slope form, that would be y minus y0 equals mx minus x0. And so I need a point, x0, y0. If I had a point, x0, y0, then I would just throw that point in. And some people are throwing in some numbers there. 1 point is 1 comma minus 52. That's right, because if I let x equal to the number 1, then y is going to be 2 minus 54, which is 52. So 1 point on the line is 1 comma minus 52. Yeah, that would work. Somebody else had a guess of 0, 0, which is a natural thing to guess. But does this line really go through 0, 0? If you want to confirm or deny whether it does, plug in the number x equals 0. Okay, so another point might be plugging in x equals 0, but would I get the output of 0 if I plugged in x equals 0? No, I would get minus 54. That's why it's called the y-intercept, right? So minus 54 is another point, right? And then somebody said another point is 30 comma 60. And that works out because if you put x is equal to 30 in here, you get 60 minus 54, which is 6, sorry. 30 comma 6 is another point. So just pick any point, just take one of those points, right? And this is not related to figure 2.8. Figure 2.8 is more of a general figure when they're trying to lay out the general theory, like the box that you see, the yellow box you see on page 82. But this particular question is not tied to figure 2.8 necessarily. It's just an exercise in making sure you know how to review the different types of equations of a line. Okay, so you know what? I'm going to pick this point just because this is an easy point for me to pick 0 comma minus 54. So if they wanted me to write it in point slope form, I would put the 0 where I have the x0 here. So I'd put x minus 0. I would put for m, I would put 2. And for the y that corresponds to that x, I would put minus 54. And since it's minus y naught, that's going to result in a plus 54. Okay, so the point slope form is right here. And I was using this circled point to get it, but now I'm going to circle the answer. Here it is in point slope form, and here it is in slope-intercept form. It's the same line any way you slice it, and if you took this form and you actually solved this equation for y, you would get that equation. So these two things are the same thing. They're just having you practice equations of a line. Really, I assigned this problem because it was meant as a review, but I know that different people saw different versions of pre-calculus, and personally, I do not emphasize the point slope form at all in pre-calculus, and so I'm sorry if this problem's giving you a little bit of trouble. Just meant to be a little bit of review. I'll go through the rest of the problem now, parts B and C, to finish up the review. Okay. Computer to the other board. Okay, so for part B now, you're going to see that there's one form. This isn't an assigned problem? Really? Oh, geez. Okay. Let's check the homework assignment. So this is problem 2.3.4, and I didn't memorize the homework assignment, but thanks for telling me that. I'm going to check right now because if this isn't an assigned problem, really you don't really need to, this isn't going to move forward with the rest of the things. Let's see, 2.3. Oh yeah, I didn't even assign this problem. Okay, all right. All right, thanks for watching out there. Thank you for letting me know that, because I was kind of questioning like why I would make you go through that, and now I can see that I didn't make you go through that. That is review. You may have seen it in pre-calculus, but what's the point? What's the slope? Haha, very funny. You don't really need to go through this unless you want to. Does anybody still want to see me finish this off, or are there other more pressing questions that you might want to ask? Because I feel like this is maybe a little bit of a silly review, because I know that you don't really need to practice that for what we're going to be learning next. The important things for you to know as we move on in learning are going to be understanding where the derivative comes from and what it represents, and understanding what it means to approximate a function using its linear approximation. So please let me know if you really want to see me do the rest of it, but I feel like since somebody just told me or reminded me that this is not an assigned problem, I don't mean to bore you or force you to do things that we don't really need to do for the rest of the class. I'm trying to minimize the amount of stuff that you need to do to move on. So I do have another question up here where somebody wanted me to talk about the properties of a linear map, and that is an important concept moving on. So I think I'm gonna go for that just to finish up this live session today. So linear maps are going to be really important when we move on. And the lines that we were just talking about, you thought they were called linear functions, and now you're going to see that in section 2.4, Alan's like, those aren't all linear functions. That's kind of a wrench in a wheel there. So let me explain that out a little bit. I also created a video for this week on section 2.4 in which I spoke to this. What I'm talking about now is what's on page 84 for linear functions. And it gives you these two properties that are known as linearity. And the big shocker there is that what we knew as linear functions over there, y equals mx plus b, not all of those actually satisfy the properties of linearity. What we're talking about here in this book for linear functions is we're talking about linear maps. And specifically, we're going to be talking about the state equations from chapter 1 and whether or not they take on a linear form in the sense of these properties of linearity. Because if the state equations do have a linear form, even if they're in higher dimensions, there's going to be some really beautiful tools in linear algebra that we're going to be able to use to describe the dynamics and predict the long-term behavior if they are linear in form. So that's why linearity is so important. Okay, and so linearity, and you'll see this in my other video too, linearity is a combination of two different properties of a mapping in general. There's the additive property, and then there's the property of homogeneity, or scalar multiplication. Okay, so the first property here says that, I'm going to use the same notation he uses in the book. If you apply the map, in this case we're going to be talking about a linear map, if you apply that map to the sum of 2 points, that will be the same thing as applying the map to the first point and then adding the map applied to the second point. So a way to say this that's common is the map of the sum is equal to the sum of the maps. That's one of the properties of a linear function in the context of section 2.4, page 84. And then the other property is that if you apply that map to a constant multiple times a point, that's going to be equal to that same constant multiple multiplied by the map applied to just the point. This first one is called the additive property, and the second one is called the property of homogeneity. If these two properties hold, it's going to be a really great time because we're going to have a lot of mathematical tools that are going to be at our disposal to work with linear maps. The whole topic of linear algebra has these two things in play. Okay. One thing that I showed in my video, but that I want to emphasize again, is that this holds, this is true for functions of the form f of x is equal to mx But it's not true. It's actually false for functions of the form f of x is equal to mx plus b, where b is equal to 0. Where b is not equal to 0. This is really important, and it's kind of a shock because it's against everything that you had learned probably up to this point if you went through algebra and pre-calculus and they talked about linear functions. It's kind of nice that I still have all that junk on the board. Do you see that? All this y equals mx plus b stuff, an equation of a line and all that. Those are linear polynomials. Those are linear, not linear unless the b is equal to 0. So if b is equal to 0 and it goes through the point 0, 0, you're good to go for linearity. If your line does not go through 0, 0, those two statements are not going to hold and it's not going to be true. So unfortunately, this more general type of form, which is sometimes called an affine transformation, to contrast it with what's being called a linear map in this context, is this doesn't obey these properties. I'm not going to go through it again because I know I already took a video. See my video for section 2.4 where I do an example. I use the function f of x equals x plus 2. And I did that as an illustration to help you out with exercise 2.4.2. So if you're having trouble with 2.4.2, I do the same thing in my 2.4 video, but for x plus 2 instead of x plus 1. Just wanted to review that again because actually these two properties right here are really going to be powerful properties moving on. In fact, in next week's learning, I don't want to let the cat out of the bag too early, but next week when we talk about derivatives as a functional mapping itself, the act of taking a derivative is a linear map. So actually taking the ddx of a function obeys the additive and homogeneity properties. And so taking a derivative itself is linear. That's going to allow us to do a bunch of special math magic to put it in layperson's terms that we wouldn't be able to do otherwise. And linear systems and linear differential equations that we'll start to explore in the later chapters, we're able to say a lot more about linear systems than we are about nonlinear systems. One thing that's particularly special about linear state equations is that we're going to be able to state the algebraic form. We're going to be able to tell you what the solution is, the exact solution. For nonlinear equations, that's not true. And if you really read chapter 1 very carefully, when he talked about the shark and tuna model, which is a nonlinear differential equations system, the functional form it's not findable. We can't figure it out. There's a lot we can do. We can try Euler's method. We can draw a vector field, all sorts of other stuff, but we can never actually state exactly what the functional form of x of t and y of t is for that. But for linear mappings, we can. So that's why these concepts are really important. I think that's all I'll say for now because I don't want to go too much further than what the exercise set was doing. And it looks like people have gotten all their questions answered. So I'll just give one chance left. Like for any of the 8 viewers who are still with me, is there anything that's missing that you still want to see me do today? I'll just give you a minute while I'm erasing the boards. And if I see another request in there, I'll happily help you out with some other problem that you want to see. Other than that, thanks for watching as usual. And I hope you have a great rest of your day. Thank you. Okay, so people are just saying thank you on there, and thank you for watching. And remember, this is collaborative learning, and so we're all on the same team, which is my favorite mode. I've never been a big fan of competition anyway. So just virtual hugs to everybody, and just hang in there and keep learning. You're all doing a great job, and we're all going to get through this together. Have a great day, and I'll see you next time. Bye.